Let's start recording. Here we go. All right. So, chapter 4, logic, truth tables. I will start this today. I will not finish. The slides are up on Leia. So, what is logic? It's the basis of all mathematical reasoning. So, math is based on logic, and automated reasoning also, right? And when we talk about symbolic logic, which is what we're going to look at in the next few lectures, it comes from an attempt to create a calculus of reasoning. So basically, the the ultimate goal historically was to create a way to compute that would do reasoning, basically. And we're not going to go into a discussion of whether we've managed to do it or not. Another thing that you should know is that the notion of computer arose from the study of logic by mathematicians. So mathematicians actually came up with the whole architecture of computers before they could actually be built. That's a totally other story. But if you're interested in these things, I can give you some nice references later on. Now, and in terms of computer science and math, logic has applications at many different levels, which is very interesting. At the very basic level, the design of machines, I mean, we're talking about logic circuits. The circuits are logic circuits, and we'll talk about that next week, I guess. If you're thinking of artificial intelligence, for example, so-called temporal logic, you want your machines to reason, so you actually have to use logic at that level. All decent programming languages have some logic built in, obviously. Something I threw in there, descriptive complexity. This is a field of research. It's fairly recent, last 30 years maybe, which attempts to understand the complexity, the computational complexity of problems from a logic point of view, and some problems that have been very hard to solve in the last 40, 50 years. Some believe that this logic will be the right way to understand these things, but that's way out of of our league here. So, and there are many other aspects of logic that we won't get into.
Sir?
Yep.
Yeah, just quickly, what's temporal logic?
Mm. Um, Logic with a built-in way of dealing with time. So the logic that we're going to look at here, the basic logic here, time is not an issue. You know, you'll see. We never talk about time, but you can create more sophisticated logics where you can encode things like never or always or sometime, that kind of thing. Obviously, if you want to be able to reason in a very natural way, then time has to become an issue. So, but I'm just throwing out there, if these are like keywords you can take a look on Google and go and see, but we're not going to look at this here, obviously.
Okay,
Okay.
thank you.
Yeah. Okay. So let's start our real stuff here. So proposition or statement, this is a declarative sentence that is either true or false. It's going to be easier to understand what this is with examples, okay? So here are what we call propositions. So Toronto is the capital of Alberta. So this turns out to be false, but it's a proposition, right? So it's a statement that can be either true or false. 1 + 1 = 2, right? Which is true. All men are mortal, a very classic proposition from many years ago. Some birds cannot fly, right? So these are statements that are true or false. Here are examples of sentences which are not propositions, which will also help you understand what a proposition is by showing you things that are not. So what time is it? That's a question, right? It's not true or false. It has nothing to do with truth value. It's a question, right? Read this carefully. This is an instruction, right? X, this is a more subtle one. This is a more interesting one. X plus 1 equals to 2. This is not a proposition because it does not have a truth value unless X has a value, right? So if X happens to be 1, this will be true. If X is 3, this is false. But until you give X a value, this is not a proposition in itself because it doesn't have a truth value, right?
So any statement that comes with a variable would automatically not be a proposition.
Yeah, in that way, yes. Although we won't go there very much, but to illustrate a more subtle point, yes, I wanted to throw that in. Here's another one. So in a sense, that's even worse, right? Because there's no equality. So x squared minus 4x plus 2 is a value, a number, or an expression, right? So it's neither true or false. So it's like if I just wrote 5, it's not a statement. 5 equals 2, that's a statement. But if there's no equality, then there's no statement. Okay, so hopefully you get at least a vague idea of what we mean by proposition or statement. So it turns out that in mathematics and in computer science, things are much simpler in a sense than in the real world. So the very basic propositions are all of the following forms. Excuse me.
Oof.
Allergies, didn't sneeze, might come later. This equals to that. So what I mean is that you have an equality and either it's true or it's not, right? So this is a what we call a basic or atomic proposition. Another one that is standard is this is an element of that. So we saw sets last time, and we can say that an element, we have an element of a set or not, right? So this is either true or false. But it turns out that in math, you can write down everything in math in terms of these basic propositions. So, okay. Now, what we'd like to do is to combine basic propositions, which are very, very simple, a little bit like those, and to create more complex ones, to be able to say more complicated things, right? So how do you do that? You take these basic propositions and you combine them with what we call logical connectives, okay? So you can create compound propositions from these basic propositions. So in the next few slides, what I'm going to do is to define the very basic logical connectives, which you may have seen before or not, makes no difference. And they might look familiar if you looked at what we talked about on sets. You'll see that there's a very, very close connection to what we saw when we looked at union, intersection, complement. Essentially, these are the same things, but said in different ways. Okay, so to discuss these things, what I'm going to do is I'm going to use Boolean variables or propositional variables. So these take the place of a proposition, which can be either true or false. So you can see it as a Boolean variable. If you've programmed a little bit, you may have programmed with Boolean variables. So it's either true or false, okay? So let's start with the very simplest one of all the logical connectives. It's called a connective, even though it doesn't connect two things. It actually applies to a single proposition, okay? It's the negation. So let's say you have a proposition P, or see it as a proposition or a Boolean variable, either way. So the negation of P, and that's, there you see the notation for this, it's read not P. This is the statement, it is not the case that P, okay? And to define properly the truth values of the new proposition or statement, we give what we call the truth table. Okay, so if you look at this table, under P you see true and false. So these are the two possible values for P, and then you define what not P is in terms of the values of P. Well, as you would guess, if P is true, not P is false, and if P is false, not P is true. So that's as simple as it gets, right? Here's a little example, which I took directly from the book, I guess. If P is the statement, Bob's PC runs Linux, then the negation of P or not P is Bob's PC does not run Linux, right? So that's the natural language way of interpreting this, okay? About natural language, I said that basic propositions in math are, this equals to that, or this is an element of that. What is great about that is that there's no ambiguity. When we start using natural language, we might run into some ambiguity. And I'll talk about that in just a few minutes, because natural language is a bit more flexible than mathematical language. Okay. Next in line, which is after negation, I guess this is the easiest of the logical connectives, is conjunction. So this one actually connects two propositions. So if I have two propositions, P and Q, the conjunction of P and Q, and it's written P and Q, this pointy thing is and, okay? So this is the proposition which is true exactly when both P and Q are true, okay? So otherwise it is false. So here's the truth table. So on the left, you have the possible values for P and Q. So there are four possibilities, right? Both P and Q are true, they're both false, or one is true, the other is false, and that could happen in both directions, right? And on the right, you have the values for P and Q. And as we said, this is how we define it. We declare the conjunction to be exactly this. So it is true when both P and Q are true, and otherwise it's false. Okay? So P and Q is true if both P and Q are true. Okay, so here is an example. If P is the statement, Bob's PC runs Linux, and the statement Q is Claire is tall, then P and Q is the statement, Bob's PC runs Linux and Claire is tall. Okay, so if it's not true that Claire is tall, then P and Q will not be true, right? Now you see immediately, just by the way, just a little aside, Claire is tall. Is that true or false? Well, depends what you mean by tall, right? I mean, she might be like 7 foot tall. Then I guess most people would say she's tall. But this is, you have to precisely define what you mean by tall, right? So that's another way that natural language is not precise, but that's another story. Next in line, disjunction.
Sir,
Oh, yep.
can it be any other letter or it's only P and Q?
No, I just chose, no, it could be anything.
Okay,
Yeah.
okay, good.
Yeah. Okay, so disjunction. This one is a little trickier because of natural language, and I'll talk about that in just a sec, okay? But here is the mathematical definition of disjunction. If I have two propositions, P and Q, the disjunction of P and Q, which is read P or Q, this is true when at least one of P or Q is true, okay? So here's the truth table. You see that this thing is true almost all the time, basically, as long as one of P or Q is true. So then here both are true, it will be true, okay? So the only time that it is false is when both P and Q are false. So P or Q is true as long as either P is true or Q is true, or both, okay? This is important. In natural language, we have a tendency to say, well, either the sun is shining or it's raining. We use the or as what we call an exclusive or, which we'll see a little later. But in mathematics, the disjunction is an inclusive or. So both, if both are true, then or is true, okay? So example, and I use the same silly example. If P is Bob's PC runs Linux and Q is Claire's tall, P or Q is Bob's PC runs Linux or Claire is tall. Oh, I have some chats here. Yeah, okay, yeah. All right. Yep. Okay, now, what's remarkable is that these three connectives, negation, disjunction, conjunction, with this, you can express all possible truth tables. It's a bit difficult for me to explain what I mean by this right now, but think that essentially anything you can say in a logical way can be said only using these connectives, okay? So in fact, you could build a machine, a computer, using circuits that mimic these three things, and that would be sufficient to build any computer, okay? That's one way of saying it. But that's not very convenient, okay? Not for humans anyway. So what we're going to do is that we're going to introduce a few more connectives, which can actually be expressed in terms of these three that I've introduced, but they are useful to know, okay? So the connectives, there's exclusive or, XOR, implication, also known as conditional, and the biconditional. So I'm going to present these right now. So here we go. Yep. Hello. Okay. Exclusive or. So this is like the or, except that if both P and Q are true, then we declare the exclusive or to be false, as its name specifies. Okay, so if I have two propositions P and Q, the exclusive or of P and Q, which is denoted as you see with this plus with a circle, it's read P XOR Q. This is the proposition which is true when exactly one of P or Q is true. You need exactly one to be true. Okay, so there's the truth table. So you see that if one of P or Q is true, the other one is false, then P XOR Q is true, and otherwise it is false. Okay, that's the way we define it. We decide that this is the exclusive or. Okay. Okay, hopefully that's clear. So this is the same as or, except that it's false when both are true. Okay. We'll get back to those later anyway. We're going to revisit these in many different kinds of contexts. Next, the conditional. This is, okay, so in math, in a sense, this is by far the most important connective. It's like the fundamental connective in math, in mathematical reasoning. It is also, unfortunately, the hardest one to learn. Okay, so I'm going to spend a little bit more time on this one. Okay, but it's like if you understand this, if you get used to this and understand this, you'll have made progress with your brain. Okay, this is like super important. So what is the conditional? Okay, so if we have two propositions P and Q, okay, the conditional, which is read if P then Q, has the truth table, which is right there. So for now, this doesn't really seem to make any sort of sense. It's just a bunch of truths and false, right? Truths and falses. Okay, so I'm going to try to explain a little bit what we want from this connective, okay? Unfortunately, there's a whole bunch of different terminology for everything surrounding this connective, okay? So in a conditional, P is called the hypothesis. So we're saying if P then Q, right? So P is the hypothesis and Q is the conclusion. So that's okay. That's fine. There are other ways of reading this. I'm not going to go there. If you look in the book, there are probably exercises that have you, and I might have assigned a few of them, but I'm telling you right now, I'm not going to insist on this very much, okay? But be aware that you might see these other ways of reading this, okay? So if P then Q can also be read, P implies Q, I tend to use that, okay? So these two I use. Another way of saying this, that P is sufficient for Q, I don't use that very much, and I won't use it here, okay? And another way of saying this is that Q is necessary for P, okay? And again, I'm not going to use this very much, okay? So now let's discuss what this is about, okay? So the intuition behind this connective is the following. Essentially, the key point is that if you have a false hypothesis, it is correct reasoning to deduce anything, whether it's true or false, okay? So in other words, if P is false, then the statement, if P then Q, is considered to be true, and it makes no difference what Q is, okay? So another way of saying this is that the only way that if P then Q can be false is if you start with a true hypothesis, P, and you want to deduce something false. Okay, so if you're trying to deduce a falsehood from a true hypothesis, this is incorrect reasoning. So then if P then Q would be false. Okay, so that's
is there a written example that you could show us? Or?
Yeah, I'm gonna give you another example, a different way of seeing this, which I think helps a lot. Okay. So if I say if 0 is equal to 1, then 5 equals to 17, then this statement is considered true, okay? Because intuitively, if you want, is that I'm making the hypothesis that 0 equals to 1, and once I make that hypothesis, then anything goes, right? So to deduce that 5 equals to 17 from 0 equals to 1 is correct reasoning. It's fine. I'm allowed to do that, okay? On the other hand, if I say if 1 plus 1 equals to 2, then 5 equals to 17, then that's false. And intuitively, right, this doesn't make sense, right? Because I'm starting from something which is true, 1 plus 1 equals to 2, and I want to deduce that 5 equals to 17, which is false, right? So this is incorrect reasoning. So we consider
Wouldn't it be
this.
true then?
Sorry?
No, it would be false.
Would it be
It's
false?
still because
false.
again, I think a good example for everyone would be look at P. P is a hypothesis, meaning if it's false, you automatically say your whole sentence is false. Your whole statement is false. Your whole statement has to be false. Like the first one, 0 equals to 1 and 5 equals to 17. If P was true, then it can't be, the other one can't be false.
Yeah.
It literally, the whole statement has to be together, like all false or all true. Or the other one.
Yeah.
Actually, no, for me it makes sense. For me it makes sense. It just can't be true or false.
Yeah.
Because P is your hypothesis.
I'm going to give you, sorry, I'm going to give you another way of seeing this, which is closer to reality, which might also help you, which I like, okay? So suppose that Bob makes the following statement, okay? So Bob says, if I'm elected, then I will lower taxes. Okay, this is the statement that Bob makes, okay? So if Bob is elected and lowers taxes, then he said the truth, right? So he said, if I'm elected, then I will lower taxes. He was elected, he lowered taxes. Everybody's happy, Bob said the truth. Now, suppose that Bob is elected, but does not lower taxes. Then people will say he lied, right? You said that if you were going to be elected, you would lower taxes, but you didn't lower taxes. You're a liar. Bob is a liar. So this is a false statement, okay? So far, so good. Now, suppose then, what's the other possibility? Is Bob is not elected. did Bob lie? He said, if I'm elected, then I'm going to lower your taxes. But he wasn't elected. So did he lie? No. He just said that in the case where he was elected, he would lower taxes. He was not elected, so you can't say that Bob lied, right? So that's another way. I mean, I'm not saying this is the interpretation of the connective. This is a way of remembering how it works, right? This is okay. Oops, sorry. So hopefully that's a different way of seeing it, okay? But which helps to remember the definition of the connective, okay? All right.
Sir?
Yep.
Yeah, just quickly. So
Mhm.
you wrote P conditional with Q. So basically it all depends with the first run, right?
Yeah. I mean, it depends on both, right? If you look at the values there, it really depends on the truth value of both P and Q. But you can split it up into two cases, which makes it maybe easier. The way I see it is this, okay? Look at the two bottom rows here. When P is false, then it doesn't matter what Q is. The statement, if P then Q, is true, okay? That's the
Yeah,
two bottom lines, right?
it sounds counterintuitive to have two false propositions, and out of that you have a truth.
Okay,
Like the
but
bottom row.
okay, if I'm a hippopotamus, why did I choose hippopotamus? If I'm an elephant, then
Okay.
if I start with the hypothesis that I'm an elephant, then anything goes, right? So we're not saying, okay, I'm not an elephant. Okay, so so that is false. But if I say, if I'm an elephant, then whatever. And that
Okay, so
whole, it's the truth of the whole statement that we're
okay,
taking
okay.
globally, right?
So
Even
it's
if
not
even if
really
it's
about
false.
the propositions
Yes,
itself.
the whole
Okay,
thing.
okay.
Yes.
Thank you.
Yeah. Okay.
So pretty much you could bypass logic with this. By what I mean is if the statement is false, it doesn't matter if it's false. As long as both of them are false, it's true. Because logically speaking, if you say you're an elephant, that is logically speaking not true. Then it's still true.
I mean,
I don't know. I'm
we're talking about the
overthinking it
truth of two
properly.
different things here. There's the hypothesis P,
Yeah,
and there's the statement if P then Q. These are two different things.
yeah.
So the only thing I'm saying is, okay, this is a definition. You can just take it for granted, and that's the definition. I'm trying to, on the one hand, illustrate why we're defining this way. And on the other hand, I'm also trying to give you an example how to remember it, okay?
Okay.
Okay, so, but you have to be careful not to confuse the truth value of P, the hypothesis, in this case, we call it P, and the truth value of the whole statement, right? So what I'm saying is, if the hypothesis P is false, if you look at those two last rows here,
Mhm.
right there, then the statement, if P then Q, the whole truth value of the statement will be true, whatever Q is. It makes no difference. That's all I'm
Yeah.
saying.
So the second your hypothesis is false, it automatically automatically it's always true. Your
Exactly. If the hypothesis P on the left
yeah
here is is false, then the whole statement, if P then Q, is
is
true.
automatically true.
Correct.
Okay,
Yes.
makes sense now.
All right. I got another chat. Okay, good. All right, so let's go. Hello. Why are you okay? Okay. All right, biconditional. This one is actually a little bit simpler. There are many ways of connecting the biconditional to the conditional. I'm not going to discuss this right this minute now. I'm going to do this next time. But the biconditional is actually has a very simple truth table. Okay, so how do we read this? It's read P if and only if Q. Okay, and if you look at the truth table, you will see that P, if and only if Q is true, when the truth values of P and Q are equal. Okay, so if you look at this table, this is exactly what's going on. So P, if and only if Q lights up true when P and Q have the same truth, if they're equal, right?
Okay, so both example, you have a false. P is false. The other one has to be false to be true.
Yeah.
And the
So
same thing is reverse.
yeah.
If it's true, the other one has to be
Yeah.
true.
So P,
Okay.
if and only if Q, if you want to see it as a test, it tests if P and Q are equal. So it lights up true if they're equal, otherwise it's false. That's okay. So that's the biconditional. Okay. And this is what I'm going to end on today. Okay. So when we're writing logical expressions using the connectives, it's a little bit like plus, minus, product, division. There's a convention on which has highest precedence. Otherwise, we'll have to put brackets all over the place, and it becomes very, very cumbersome. So the convention is that negation has the highest precedence. So that's the first one which is applied. It has higher precedence than and or. Okay. So for example, the example I wrote here, if you read not P and Q, the negation there does not apply to P and Q. Negation applies first. Okay, so it's not P, all of that, and Q, which makes a difference, right? It'll make a difference. If you compute the truth table of this, of not P and Q, rather than not P and Q, you will see that there's a difference. Okay, again, if I write not P or Q, then it stands for not P, all in that in bracket, or Q. Okay. And next time I will continue with logical equivalence. For now, I'm going to let you work on, so the WebWorks hasn't, I'm going to modify the WebWorks so that they open right now. Okay. So I'm going to do that. And are there any other questions or comments?
So pretty much the rest of the class is just dedicated to do those 5 webworks.
Yeah, so yeah. I'm gonna go right now and change the their starting time to right now. Okay.
So they're based on the last class, and I'm guessing this class as well.
Last 2 classes. Yeah.
Okay.
Yeah.